are some supplementary. In fact, you can have a look at the chapter 4, list files, but I have made the content separately. The topics we are going to talk about is the second to the last one, according to the files in the class materials folder. It's a hardy closed, so we will talk about this one. And for the pumping system, this one I think we had talked about last week, and we are 100% completed ใช่ไหมเราพูดเสร็จจบหมดแล้วใช่ไหมฮะ pumping system เนี่ย Anyway, I think we have completed. So now what we had left just only this one. So actually part of this presentation is there in the files CE 04, but I just make it give some example so that I put it in this file separately. So the piping system, so I think you have already studied about the piping systems intensively in fluids mechanics or maybe in the fluids, in the hydraulic engineering. So I will not go into the details again, so I will not talk about the backgrounds again, but just I'll pick up some issues which really related to the water supply engineering work, which is the pipe network. Piping systems, actually we have used the pipe in several formats. Sometimes we have connect more than two pipes in series. So sometimes we connect the pipes in parallels. I think connecting the pipes in series and the parallels you have studied already in the previous course. So talking about the pipe, so I'm now on the OneNote screen. So talking about the pipe connections in series, so if we have two pipes like this, pipe 1, the diameter is bigger than the pipe 2. So this is the inlet and this is the outlet. According to the characteristics of the pipe connected in series, hopefully you can still remember. If we measure the energies in between these two pipes, of course, while the water passing through the pipe, there might be some loss. So this is the loss due to the pipe number 1. And then the second pipe, while there is a flow, so there is loss due to the pipe number 2, like this. And if you still remember, according to the characteristic of pipe connecting in our series, you will find the total loss is equal to the summations of the loss in each pipe. So in this case, the loss in the pipe number 1 combined with the loss in the pipe number 2 will be equivalent to the total loss. So this is the fourth characteristic of the pipe connected in series. And then the second one, considering the flow rates. The flow rates entering to the systems in these two pipes. So the flow rates entering to the system will be equal to the flow rates flowing through the pipe number one, and also the flow rates flowing to the pipe number one is equal to the flow rates flowing to the pipe number two. But the size, pipe size are different. The flow rates are still the same. As we all know that the flow rate is equal to A into the velocities V. So if the diameters, pipe diameters is smaller, the velocities will be just increased. But if the diameters is larger, the velocity will be smaller. That is why the flow rates through the pipes number one and the pipe number two are equal. So these are the characteristics of our two pipes connected in series. And what about if we have several pipes connected in parallel, like this? Suppose we have three pipes. This is the pipe number one, number two, and number three. So this is the flow rates entering to the system and leaving from the system. So considering the head loss to the pipe, of course, the diameters of the pipe number one may not be the same as the diameters of the pipe side number two. So these three, the diameters are different. If you measure the head loss in between each pipe, you will find the loss in the pipe number one will be equal to the loss in the pipe number two, and also the loss in the pipe number three. So the loss of these pipe are the same, but just the flows, the flow rates may be different. The flow rates are in the pipe number one, if you combine with the flow rates in the pipe number two and the pipe number three will be equal to the flow rates in the influence and in the effluent, like this. So this is the characteristic of the pipe connected in series. So these are what you have achieved from the starting of the fluids mechanics and probably the hydraulic engineering. So what we are going to talk about today, the thing is when we distribute the water from water treatment plant to each individual houses, we will not use just only these two connection, two types of these pipe connections, but very often and probably mostly we use the pipe connected in a network. Mostly we line the pipe along the road and then connected them with each other like this. So the inlets maybe get into the network here, and then the outlet may be almost everywhere in this pipe network. So this system is a little bit more complicated as compared to the previous two types of the connections. For these two, we have already discussed about the characteristic in terms of the head loss relationships and also the flow rates. But talking about this one, in fact, in the hydraulic labs, not the fluids mechanics labs. In the hydraulic labs, there is one experiment. So if you are taking this course, you will have to conduct the experiments called the pipe network. they have actually made a simple loop like this. I think I've just realized that for those who are actually enrolled in 2560, your ID number, if the student's ID begins with 6 zeros, you have to take both fluids mechanic labs and the hydraulic labs. So this is for the students with the ID number begins with 60. But if the ID number begins with 61, we have just revised the curriculum a long time ago, several years ago, actually. For the students begins with the ID number 61, so you only study the fluids mechanics, but you don't do the hydraulic engineering labs. But I'm not sure how much the contents of the fluids mechanics labs change, or maybe they will combine these two together, or maybe some contents of the labs will be cut off. Last week, I was also talking about the pumping system. So in the labs, you will have to determine the pump curve. You have to investigate at various flow rates and the pump curve. So at the end, you should be getting something like this, the curve. So if you have like two pumps connected in series, you should get the curve like this. And if you have two pumps connected in parallel, you should get the pump curve like this, so that the flow rate is double in case of the two pumps connected in parallel. But if you have two pumps connected in series, the head will be double. So this is what you have to do it in the lab. But I'm not sure whether these labs and also the labs that I'm going to talk about are still there or not. But unfortunately for the students who the ID begins with 61, you will not be able to study the hydraulic engineering laboratory anymore. But anyway, talking about the lab, they have just provide you the very simple looping system. I'm not sure why I cannot erase this line. In fact, this is not the permanent marker, but I don't know why. Okay. Maybe there's some problems about the software. As OneNote is actually fabricated by the Microsoft, but the computers that I'm using is the Apple. Sometimes it's creating the problems. Okay, now it is working. The labs is something like this. So they have prepared you to work on such a very simple loop, just one loop. There are 4 pipes connected like this. This is the pipe. Suppose it's a pipe A. This one is B, and this one is pipe C, and this is probably pipe D. And there's one inlet here. So the flows are entering to the piping system at these positions. And there are 3 outlets. This one. So this is outlet number 1, and this might be the outlet number 2, and this might be the outlet number 3. So it will be something like this. Very simple looping system, just one loop. But this one is a little bit more complicated. According to the figures I sketched, you see we have 6 loops. Okay. According to this one, if you really have a look at the entire system, if you really have a look at the entire system, so suppose this is the boundary condition, you will find the flow rates, the relationships amongst the inflows and outflow. We can actually say the flow balance. According to this system, so the inflow is equal to Q1 plus Q2 plus Q3. So this is what we have learned from this system. The flow rates inflows must be equal to the outflow. So this is what is so-called the flow balance. If you consider at each point, the points where there is the pipe connections and also the inflows or the outflow. So at these points, we generally call a node. Okay, so we generally call node. This node is more or less the place where we join the pipes or where there is the inflows or the outflows. So at each node, there must be some problems with the applications again. Okay. Why I remove this? Some of these contents are not moving along with the above contents. Okay, so at each node, suppose this is the node 1. This one is number 2, 3, and 4. So at the node number 1, just consider at the node number 1, there is the inflow called Qn, and there are 2 pipes connected. So the flow rates flowing to the pipe A, so I'll just give it as the QA, and the flow rates flowing to pipe C, so I will just put a QC. So at the node, summations of the flow must also be equal to 0. So this is the characteristic of the pipe connected like this, the pipe network. So why I'm saying summations of the flows at each node is equal to 0. So if I give like a flow entering to the node, it designates as the positive, and the flow leaving the node is defined as the negative. So positive must be equal to the summations of the negative, so that summations of the flows is equal to 0. That's what I'm trying to say. So in this case, according to this we can say like a Q in is equal to QA plus a QC. So this is at the node number 1, and at the node number 2, this is the QA, and this one is a Q1. So for a B, pipe B, so I assume the flow rates along with the pipe B will move from node number 2 to the node number 3. So this is the directions of the flow. According to this node number 2, we can actually say like a QA, it's equal to Q1 plus Q, this must be a QB, like this. What about this one? So I just assume the directions of the flow. So for this one, QB plus QD must be equal to Q2. And the last one, QC must be equal to Q3 plus QD. So summations of the flows at each node must be equal to 0. This is one of the outstanding characteristic of the pipe network. So you can apply the same rule while considering the complicated system like this. Okay, but this one is just what you have to do it in the hydraulic lab. So you have only study a very simple loop, just one loop. But in reality, there are a number of loops, unaccountable number of loops. This is the characteristic of the pipe connected in series like this. But what about the loss, the head loss, or the energies at each node? The energy at each node must be the same. So if everything is going correctly, so the energy at each node must be the same, no matter the flows coming in or the flows going out from the node. So I was just trying to sketch the loss due to the flow at each node. So at node 1, probably I used the blue to represent the energy at this node. So this is the energy levels at the node 1. Remember that when we talk about the energies, it means that I would talk about the three terms in combination. The energies due to the elevation, which we usually call the elevation head, plus the pressure, plus the the velocity head, 2G. So if you compare with the energy at probably the node number 2, so this must be equal to the energy at the node number 2. So this is at the node number 1, P2 divided by gamma plus V2 squared divided by 2G, and of course plus the heat loss which occur due to the flows along the pipe. Now we are considering the flows through the pipe A. So if I sketch the energy grade line, of course there might be some loss. So there might be some loss. This is the head loss due to the pipe A. So this is the magnitude of the energy measured at node number 2. And from the node number 2, the flow moving further to the node number 3. The energy beginning from node number 2 must be the same as the energy left after the flows coming from the node number 1. So this is the starting point. Then again, the energy still dropped due to the head loss. So this is the energies at the node number 3. Okay, this is the energies at sorry, this is number 3. Okay, this is number 4. So there will be some certain loss here, and again there will be some certain loss due to the flows through the pipe at D. So this is a kind of energy grade line, or the hydraulic grade line. Okay, so the hydraulic grade lines are the loss in fact you can use the Parsons-Williams equation to determine the head loss. Okay. This is the second characteristic of the pipe connected in the network. At each node, the loss, the energy levels will be the same. Even there are flows entering the node from more than one point. Okay, so this is the characteristic of the pipe connected in series. The thing is, while you're determining the head loss, what we really want to know is we really want to know the flow in each pipe. We want to know the flow rates in the pipe A. We want to know the flow rates in pipe C, D, and also the pipe B. So once you know the flow rates flowing to these four pipes, you can only determine the head loss. But in the labs, you will have some way to measure. But in these lectures, you will have to find, you have to use the analytical method to find out what will be the flow rates flowing through each pipe, so that we can determine the head loss. So you can estimate the head loss at the node number 3. So at this node, you can determine the head loss. So if I ask you how much the energy left at point 3, at node number 3, if the flows begin from the node number 1. So if I ask you like this, you should actually take the calculation. So you should calculate it. So if you want to measure the loss of the flows from node number 1 to the node number 3, so the head loss should be equal to the loss due to the pipe A plus head loss due to the pipe B. So you can measure it like this. Alternatively, as we are connecting the pipe in a network like this, you can calculate, you can determine the flow rates in the other way, as we are connected this pipe in a loop, so that you can also determine the head loss by taking the loss in a pipe C plus the loss in a pipe D. So at the end, it will be equal. Loss in a pipe C may not be equal to the loss in pipe A. Okay, loss in pipe D may not be equal to the loss in pipe B. But anyway, combinations of the loss in pipe A and B must be equal to the combinations of the loss in pipe C and D. At the end, so it will reach the same loss. Okay, so this is the characteristic of our system. So this is what I was trying to explain, just based on the simple loop, and also based on what you have studied in the lab. But the problem is talking about the real situation. So what kind of methods we have to use to determine the flow through each individual pipes, as the system may be more complicated, not just one loop like this. So now we are going to talk about the method that we can apply to estimate the flow rates in each pipe. Okay, I will just come back to the presentations. These Hardy-Claus presentations again. Piping systems, there are some certain concerns guideline. The flow, a maximum flow synchronized should not exceed 1 meters per second with the upper limits of 3 meters per second. In fact, we prefer not to maintain the flows greater than 3 meters per second. But in general, one in between 1 to 2, it's the most appropriate. So if we maintain it at higher flow rates, then there will be the higher head loss. If you connected pipe with the pumping system, so the pumps has to work a lot to achieve to overcome the loss due to the high velocities. Here, I think you can study because it's really similar to what you have studied before. Okay, just come to the method that we are going to apply to determine the flow rates in each individual pipe connected in the network. The methods that we are going to use is actually called the Hardy-Claus method. It is actually called the Hardy-Claus method. The energy loss at each pipe in the elements I actually means the pipe. So as we have many pipes, that is why we call it the elements. And I may be ranking 1 to too many. In general, we can say like the head loss it's equal to the constant depending on the pipe diameters, length, times, and conditions, multiplied by the flow rates flows in that element to the power of x. So this is the general terms of the energy loss determination. So it must be equal to the flow rates into the constants. So constants depends on the pipe diameter. According to this equation, so what is x? X generally it might be 1.85 to 2, depending on the equation used. So what does it mean? If you really come back to the previous presentations, are maybe this one, the pumping system. I have introduced you two equations we can use to determine the head loss. The first equation you really are familiar with is the Darcy-Weisbach equation, this one. And the second equation I have just introduced you is the Parsons-Williams equation, this one. If I substitute velocities by the flow rates divided by A, as the Q is equal to AV, right? So that V is equal to Q divided by A. So V is equal to Q divided by A. So if we substitute and we express the flow rates in terms of the flows, for the Darcy-Weisbach equations, you will get Q to the power of 2Q square. And for the Parsons-Williams equation, so if you substitute V equal to Q divided by A is the cross-sectional areas. Generally, if we use the cylindrical pipe, the diameters must be pi d square divided by 4, right? So for the Darcy-Weisbach equation, here is a 2. But for the Parsons-Williams equations, Q to the power of 1.85. That is why, according to the loss determination, the flow rates to the power of x x refers to 1.85 or 2, depending on the equation used. And what about k? K is the constant, so it's a combination between it's the combination of the length, diameters, and other friction loss coefficient, friction factor, or the Hardy-Claus constants, friction constants. So those are a combination of these parameters is represented by the k, the values of k, and k of the elements I, it's given as like this. So in general, we can say like the energy loss in the elements I is equal to the constants into q to the power of the x. But in this cost, as I mentioned previously, so for water, especially for water supplying, we prefer to use the Hazen-Williams coefficient so that x must be 1.85. In the determinations of the flow, so we are going to determine the actual flows in each element. So the actual flow must be equal to the assumed flows plus the required correction. The procedure is like this. Initially, you have to assume the flow, and then you have to determine the required correction, which is delta. So the assumed flows plus the delta, you will get the actual flow. This is the method. Okay, this is the procedure. If you want to determine the flow, so you have to properly determine from this head loss. You have to verify from the head loss equation. So there are some certain methods that you can do it. As we have so many pipe, so we can actually substitute this flow rates. Q is equal to QIO plus delta. So you can substitute this Q into the previous equation. QI, you have to make a QI equal to QI0 plus delta. Substitute this one into the previous equation, this equation. Then you will get this term. It's a little bit complicated terms, but anyway, for any loops, summations of the head loss about the loop must be equal to 0. Summations of the head loss about the loop must be equal to 0. So as I mentioned previously, the loop in fact, if you measure the head loss from pipe A and pipe B, and then you are taking another head loss from C, B, C, and D, the combinations, if you put the sign, so it will be equal to 0. Okay. Anyway, so we can make it like this. Summations of the head loss is equal to 0, so that summations of this one equal to this one equal to 0. So as this equal to 0, so we can move this one to the other side, and then divide this size by this one, you will get delta. So delta is given as this one. Summations of the k, q divided by summations of x, k, and q to the power of x minus 1, like this. And at the end, we will get delta equal to minus our summations of the loss in each element divided by x into summations of the loss in each element and divided by the flow rates. So this is the corrections. So once we get the corrections value, then we substitute this corrections value combined with the assumed flows till we get the actual flows. The thing is, as we begin with the assumed flows. So sometimes even we try the first time to determine the delta, but very often we never get the actual flows because the delta is still greater than the acceptable limits. So the assumed flows will close to the actual flows only when the delta is very small. Okay, so at the end, as the first trial, if we are still getting the delta in a greater number, it means that the actual flow that we obtained is still not acceptable. So we have to do the second trial to determine the delta again. So it's just like this. So the first time you determine delta. So the first time you assume the flows, you determine delta, then you get the actual flows. And again, you take the actual flows from the first trial and use as the assumed flows in the second trial. So for the second trial, you get the actual flows from the you get the assumed flows from the actual flows obtained from the first trial, and then determine the delta. So you do it again, maybe 3 to 4 times until the delta we have got is very small. Generally speaking, we can say like less than 10% of the initial value. Okay, so these are the procedure we determine the actual flows. But anyway, it's a little bit complicated, and you probably cannot figure out what I'm explaining about the procedure. So it is better if we could start with the example so that you can see how we can actually determine the flow rates in each individual pipe. If you scroll down these presentations, you will find the example 7.1. So in this example, you have to find out the flow rate in each pipe, the diameters and the distance or the lengths are given. The pipes are connected like this, so just have a look at this figure. Explanations are quite long, but just have a look at this figure. So in this figures, you see the pipes connected in a network. The inflow to the system entering to the system, the flow entering to the system at point A, and at each point or each node, there will be some outflow. This is point A, and at point I, 2.2 cubic meters per minute. You can. This is the flow rate. The water used flowed. At point H, another 2.5 cubic meters per minute is used. At point B, 2 cubic meter per minute. G, 14 cubic meter per minute, and F, another 2.3, D, 1.5, and C, 0.5 cubic meters per minute. So here there are a number of point of use. So the point of use, combinations of the point of use must be equal to the inflow. Okay, so combination of this 2.2 plus 2.5 plus 14 plus 2.3 to 1.5 and 0.5. A combination of these flow must be equal to 25 cubic meters per second according to the flow balance. So these are according to this distribution system, you can find several pipes are connected in and becomes a network. So basically, according to these figures, you will see three loops. You will see three loops. This is the loops number one, and this one is the loop number two, and the last one is the loop number three. You will see at least three loops. Okay, each loops there are pipes connected. AI, AB, IH, BH for the loop 1. And for the loop 2, there are several pipes, HB, BE, and the next is EF, FG, and the last one is the GH. So the loop 2 consists of 5 pipes, and for loop 3 consists of only 4 pipes, like this. So if you want to determine the flow rate in each pipes, so you have to follow the methods called the Hardy-Closed. And according to the method, you have to, when you do the analysis, you have to consider the flow through the pipe. You have to first assume flows in the pipe. For example, at point A, I don't know what's wrong with this one.มันเป็นอะไรของมันเนาะเวลาเรา move บางอย่างมัน move บางอย่างมันไม่ move ถึงแม้ว่าจะขึ้นหน้าใหม่ไอ้นี่ก็ยังมาด้วย okay, I'm not sure. What if so I just tried another way to and use another application. Okay. So before determining the flows at each pipe, you have to assume the flow rate. Let's begin with the point A. So this is the point A. At point A, here there is the inflows of 25 cubic meters per minute. So this is the point A. You have to assume. So if it goes to point B, how much would that be? Suppose this is okay. So this one, the diameter is 4.05 405 millimeters. This one is 305 millimeters. It's roughly about the same, so you can assume it's like a 13 cubic meters per second, but this one may be 12.เดี๋ยวนะมันค่อนข้างที่จะไม่ค่อยเป็นไปตามที่คาดเท่าไหร่นะSo this is something different from the equipments that I used at the office. Okay, so you can make like this one is 13 and this one is the 12, and you can make another flow rates in other pipe. You can assume the directions, any directions you want, because at the beginning we are not sure which directions they are moving. You can assume at any directions. This is the first thing you need to do, and then assumes the flow. So if we are thinking this one is the 12 and flowing to the node I like this. Okay, so this is 12, and at point I, at this point, this is 12, and this one is the 2.2, so that you can estimate the flow rates at in pipe IH. Okay, this one is the 12, and the other two are the flow leaving the node I. So combinations of these two must be equal to 12. So if this is a 12, then the flows going to the pipe IH must be equal to 12 minus 2.2. So it becomes 9.8, right? It becomes a 9.8 if we are taking like this. And at each pipe, you have to estimate the flows accordingly, and also the directions. And when we do the analysis, we will assume again the directions in each loop. If you analyze the loop number 1, the flows that goes into the clockwise directions, so you may give a positive. The flows moving against the clockwise, or the flows to the counterclockwise direction, so you give the negative. So if you are about to analyze each loads. But the problem is, just have a look here, the common pipe B. So this is the common pipe BH. This is the common pipe BH, and if you consider the loops number 1, BH moving like this, it's corresponding with the directions of the positive signs we had given. So with respect to the loop 1, BH is positive. But with respect to the loop number 2, the clockwise directions is positive. But the directions of the BH is against the clockwise directions, or it goes in the counterclockwise direction. So in the loop number 2, BH will be a negative. So for the common pipes could be a positive in one loop, and it could be a negative in another loop. We have two common pipes, BH and BE. BH is the common pipes between the loops 1 and the loop 2. BE is the common pipes of the loop 2 and the loop number 3. So this is we have to set up before do any further analysis. Then we put all the informations in a table. So in the table, what we have to do, we have to assume the flows. So the flows in the first columns are actually second to the left. You have to put the assumed flows. For example, AB, this one, point A to point B, we have to assume it's like 13, and A to I, we assume to be a minus, 12, but it gets minus because the directions is against the positive of the positive directions, or is against the counterclockwise directions. And BH, we assume it's 3, and HI a minus 9.8. Okay, so this is the loop 1, and we also have to do the same thing for the loop 2. The loop number 2, there are 5 pipes. BH here is the common pipe. So if you really take a look at the BH again, you will get the flows that you assumed. In fact, it should be equal or slightly different. Here they made a 2, but in fact you can actually make a 3. It doesn't matter, but I'm not sure according to this reference why they make it 2. Okay. Oh, just a moment, I have some urgent message. เดี๋ยวขอแป๊บหนึ่งนะฮะนักศึกษาอ่านดูไอ้ตรงนี้ไปเรื่อยๆนะฮะ Okay, so based on this, where do we left? Okay, this one, you have to basically assume the flow rates. For the first term, you have to assume the flow rates, and then the flow rates that you assume, you have to put the positive or negative signs based on the directions given here. You can actually assume like if it goes along with the clockwise directions, it gets positive. But if it's against the clockwise direction, so it's negative. That is why pipe A to piped connected part A and point A and point I, it gets negative. And this one, as the flows, we assume it goes from the point I to point H. So again, it's against the clockwise direction, so we have to put the negative here. Other loops, we also have to do the same. Okay. For the BE, it's another common pipe. You can also put the flow. If you really have a look, you will find in the loop 2, it gets positives, but in the loop 3, it must be a negative. In here, what you have to do next, the procedures, according to the procedures, you have to determine the actual Q, actual flows. In fact, the actual flows is equal to the assumed flow rates plus the delta. Delta is the correction. So according to this, you have to determine the delta. Delta, how do we find the delta? Delta is equal to the minus summations of the head loss at each element divided by x summations of the head loss from elements I to the n divided by flow. So in this case, you can use the columns to determine the head loss and the head loss divided by a flow rate. You have to do it like this. Put all the information. AB, the diameters is in fact 405 millimeters. AI 305 millimeters. Or in terms of the meters, it's 0.4. This one is 0.3, and BH is 0.25. And these are the length of these 4 pipes. And the next columns you have to determine for the slope S. So what is the slope S? The slopes is actually can be determined from the Parsons-Williams equation. So if you go back to the Parsons-Williams equations again, head loss. So just check the equations from the pumping systems presentation. Here, the head loss is equal to 6.82 V divided by C to the power of 1.85 into L divided by D to the power of 1.167. So if you moved L to the other side of the equation, it becomes the loss divided by L. L is the length of the pipe. H is the head loss. In fact, this, if you are taking H divided by L, it's also equal to the slope of the hydraulic grade line. Okay, so if you really have a look here, this is the hydraulic grade line, and then this is the length of the pipe. So the loss is given here loss. So if you take the loss divided by L, this is the loss and this is the length. If you take the loss divided by L, it's more or less the slope of the hydraulic grade line. Okay, that is why in this presentation, in the previous page, you can also find out the slope, which is equal to the loss divided by L. The slope it's equal to loss divided by L. This one, based on the Parsons-Williams equation, you are taking the flow rates, diameters, length to determine the slopes or the loss divided by L. So you take this information to determine the slope, then you multiply it by length, you will get the loss, as the head loss divided by L is equal to S. So if you multiply this one by this one, you will get the head loss. Okay, so the head loss of the pipe AB is equal to 13.75. And in the next columns again, if you take 13.75 divided by 13, which is the flow rate, assumed flow rates, you will get this amount, 1.058. We repeated the process to determine the slopes, the head loss, and the head loss divided by Q. And the slopes should come along with the positives or negative signs. And again, with the head loss, should come along with the positives and negative sign. But loss divided by Q, if you're taking this one divided by this one, the signs will be canceled. That is why it's all positive. So here, just take the summation. So if you don't get the number with the sign, you will get the wrong summation. So you have to take the summations of all these 4 pipes in the loops. Finally, we get a negative 46.42. And then another columns, the last columns, if you take the summations, you will get something 8.676. So again, determine for the delta. Delta is equal to minus summations of the loss divided by X, as we are using the Parsons-Williams equation. So X is 1.85 into summations of loss divided by the flow rates. Finally, we get this one. This is the delta obtained from the loop number 1. The same procedure must be applied to the loop number 2 and the loop number 3, like this. Then you will get the delta for each loop. Loop number 1, you get this number for the delta. Loop number 2, you will also get this number for the delta. This is the first trial. The first step, you have to determine, you have to assume the flow rates, then determine the delta. And next, we're going to find out the flow rates, the actual flow rates. The actual flow rate is equal to the assumed flow rates plus the required flow rates. Okay, so that is why you have to do it again. AB, the assumed flow rate is 13. So if you combine it with the 2.9, so it becomes 15.9. This is the actual flow for the next trial. And for the IA, the flows is minus 12. Delta is 2.9. So you have to take minus 12 plus 2.9. In this, you will get minus 9.1. In this, you will get a 9.1. It's minus 9.1. Okay. For HI, sometimes the urgent message is coming. Sorry. So I have to send the thank you. Okay. Okay, so for HI, it's minus 9.8 plus 2.9. You will get minus 6.9. But very special to the common pi, it is BH, right? BH is the 3. Just a moment. I need to repeat. Okay, for the BH, BH is very special. As I told you, it's the common pi. So for the BH, you have to take two correction from both the loop 1 and the loop 2 and combine it. So it's a 3. So the corrections obtained from the loop 1 is a 2.9, but the corrections that we obtained from the loop 2 is 1.4. So you have to take this one minus this one and take 3 plus 2.9, and as the corrections come from the other loops is positive, though it's positive in the other loops, but when you combine it with this one, you have to take a negative. Okay, you have to you have to take a negative in this case. So finally, you'll get this amount. But anyway, okay, so you have to do the same thing with this common pi BE. Okay, for the loops number 2 and the loops number 3. And finally, determine again for the delta, and the last one, deltas. And again, do it again, because the delta is still greater than what we had expected. We will do it until the delta is less than 10% of the initial deltas. So if we are getting a small delta, the smaller delta will be giving the assumed flows close to the actual flows. In fact, the delta should be small. So only just a small delta assumes flows will be near the actual flows. Okay. So we have to try it again, because after second try, the delta is still 0.4, but for the second group, the delta is 0.7. But in fact, the last loop it's quite okay. So if we try again, here you will get a delta different value. So it's just a 0.2 with respect to this one. It seems to be okay for the first loop. If you are not sure, you can do it again for the next trial. This is the third trial. Then we do it again. So if you, as you do more trial, you will get close to the actual flow. Okay, if you do it again one more time, I'm sure that you will get the deltas smaller than 0.2 for the first two loops. And the loop 3, the delta is very small as compared to the second trial. So according to the procedures, finally we come up with this figure. These figures, the first trial, we assume flows in the pipe AI 12 cubic meters per minute. For the second trial, after corrections, we get a smaller flow, little bit smaller flow. And then third trial, fourth trial, finally we come up with this flow rate, 8.5 cubic meters per minute. Same as other pi, A, B, the first trial, we get 13. This is actually assumes flows. And at the end, we are getting 16.5. So it's increased. This we first try with the 2. And finally, it comes up with 3.2. So after 4 trials, so we pick up the flow rates updated after 4 trial to for the further uses. So this is the methods called the Hardy-Cross. But just imagine that we only have 3 loops. If you have more loops, you have to use the some advanced software to determine the flow rate. But anyway, according to this example, so I have made the Excel files you can use to determine the flow rate. Hardy-Cross. It must be this one, maybe. But I just wonder that why the person who upload this file is not me. This is the Excel files. I think I have made this one. The number may be slightly different from what I had shown you in the presentation, because that one is actually the photocopies from the textbook. So I have made it again just to correct some value. Okay, so if we put the BH2 and HB is also 2, then what will happen? Finally, we get the delta here, and this one, and this one. Then for the second trial, finally we get this one. For the third trial again, the delta is getting smaller and smaller. And after fourth trial, the delta is even smaller than the third trial. So you can study this first. But I just wonder that why this file wasn't uploaded by me. Some students uploaded this file yesterday. ใครวัชรพลไปมายังไงถึงได้อัปโหลดไฟล์นี้ขึ้นมาเนี่ยวัชรพลอยู่ไหมฮะมีวัชรพลอยู่ในนี้ไหม
อยู่ครับ
แล้วไปมาทำไมคุณมาอัปโหลดไฟล์นี้อยู่
ผมแค่เปิดเข้าไปดูเฉยๆครับ
อ้าวเหรอ
ใช่ครับ
อ๋อเปิดเข้ามาดูแล้วคุณเซฟหรืออะไรสักอย่างหรือเปล่ามันก็เลยไอ้นี่
ไม่แน่ใจครับ
อะไรนะฮะ
ผมก็ไม่แน่ใจเหมือนกันครับผมเปิดเข้ามาดูเฉยๆครับ
อ๋อเหรอ
ใช่ครับ
จริงๆไม่แน่ใจเหมือนกันนะฮะเพราะว่ามันน่าจะเป็นอีกมี modify อะไรบางอย่างหรือเปล่า
ไม่น่ามีนะครับ
เหรอหรือคุณไปแอบ modify แล้วคนอื่นเอาไปดูแล้วนึกว่ามันมีอะไรบางอย่างแล้วเดี๋ยวคนอื่นคิดว่ามันถูกผิดหรืออะไรบางไปเพี้ยนไปจากเดิมนะokay so this one is actually the Excel files you can follow because it's the same as the figures that I showed you in the presentation. So these are all about the Hardy-Cross method. But anyway, I'm not sure whether I give you the last assignments relevant to the assignments มันหายไปหมด okay, so anyway, there will be the assignments relevant to the Hardy-Cross method. I'm not sure which one is the latest assignments you have got. The second one's the storage pumping system. Okay, maybe today, so I will give you one more assignments. The expected times to submit is early of next week because it must be before 10 of March. 10 of March is the first date for the midterm examinations. Okay, so according to this Hardy-Cross method, do you have any other question? มีคำถามไหมครับ
มีครับอาจารย์เปิดหน้าที่เป็นตารางได้ไหมครับตารางแบบที่เป็นในสไลด์อะครับ
slide so what are you going to ask
คืออย่างพอมาเป็นท่อ BE อะครับอาจารย์ทำไมมันถึงเป็นแค่ 7.5 เรา assume เหรอครับหรือว่ายังไง
assume firstใน first table ใช่ไหม first collection ใช่ไหม first collection assume หมดเลยฮะไอในครั้งแรกอะ
ทุกตัวเลยเหรอครับ
ทุกตัวเลยฮะแต่ว่า assume เนี่ยไม่ใช่ assume มั่วนะต้อง assume based on ไอ้ flow balance ด้วยก็คือที่โหนดต่างๆเนี่ยนะ summation ของ flow จะต้องเท่ากับ0 summations of the flow must be equal to 0 you can assume at any value but it must be based on the fact that summations of flows must be equal to 0 for example at point A so if it is 25 in flow here combinations of the flows flowing to A, B, and AI must be equal to 25, must be equal to exactly 25. But if it may be slightly different, but anyway, at the end, it must come automatically once you correct it with the delta. คือแตกต่างเล็กน้อยได้แต่ว่าท้ายสุดมันก็จะออกมาเท่ากับเดลต้าแต่ว่าไม่ใช่แบบผิดหูผิดตาคือจริงๆแล้วเนี่ยถ้าคุณดูในนี้มันจะมีตัวเลขบางอย่างที่ดูแปลกๆแต่ถ้าคุณไปดูไฟล์ Excel ไอ้ตัวนั้นผม correct หมดเรียบร้อยแล้วสังเกตดู BH ในนี้เขาใช้3นะลูปที่1อ่ะสังเกตเห็นไหมฮะเดี๋ยวผมเปิดไฟล์ผมยังไม่ได้แชร์หน้าจออันนี้ผมอยู่บนหน้าจอตัวนี้สังเกตดู BH ในลูป1เขาใช้3นะแต่ BH ในลูป2เขาใช้-2เขาใช้2คือจริงๆแล้วมันควรจะเป็นตัวเลขเดียวกัน แต่ว่าพอเขาใช้ตัวเลขที่มันแตกต่างกัน แต่ว่าท้ายสุดเนี่ยมันก็ออกมาใกล้เคียงกัน แต่ว่าถ้าผมทำใน Excel ไฟล์ใน Excel ไฟล์เนี่ยผมจะ collect ตัวเลขที่มันคลาดเคลื่อนพวกนี้เนี่ยหมดเลยเพราะฉะนั้นจะเห็นว่าตัวเลขใน Excel ไฟล์เนี่ยมัน slightly different from ไอตัวไอ table 7.2 นะฮะas I mentioned the values that I put the rectangular here it's all assumed but you have to based on the fact that summations of the flows at each individual node must be equal to 0. Combinations of the flow must be equal to 0 or inflow must be equal to the outflow. แล้วก็ไอตัว for the common pipe the actual flow it's equal to the assumed flow plus the delta but as the common pipes you have to concerns two delta from the looped one and the deltas from the another loops but when you combine you should combine in a different way so this one is the positive this one must be a negative because directions are different although at the end it comes up with the positive value อย่าง BE อย่างเงี้ยนะฮะ 7.5 BE is the common pipes in a loop 2 and the loop 3 this is BE 7.5 then you have to combine with 1.4 and then you have to subtract it by 0.1 to get this value. It might be slightly different, but if you check the Excel file, you will get everything based on what I had mentioned. So just have a look here. Other relating materials, Hardy closed the Excel files. Uh, 7.5 and here for the common pipe HB the first trial I have taken 2 this one is the -2 then for the second loop so I would take like a 2 combined with this one and minus this one so finally this is what we get 3.5 and as for the BE is also the common pipe here again if you have a look so the BE plus 1.4 this is the delta from the same loop and you have to also combine with the delta from the other loop but combine it in the other way put the minus here then we get this number so at the end you will get something close to 0 delta close to 0มีคำถามเพิ่มไหมฮะเมื่อกี้ใครถามนะเมื่อกี้ผมไม่ได้ดูชื่อ
ผมครับอาจารย์
ใครอ่ะ
จุลจิตครับ
อ๋อเหรอนะฮะมีคำถามอื่นเกี่ยวกับ Hardy Cross ไหมฮะ Hardy Cross นี่เป็นเรื่องสุดท้ายนะฮะ It's the last topics to the chapter 4 and it's also the last topics before the midterm examination so if you don't have any other question then we will move to the next chapter มีคำถามไหมฮะเรื่องปั๊มส่งกันบ้านหรือยัง ปั๊มนี่ assignment เรื่องปั๊มนี่มันส่งไปแล้วใช่ไหมการบ้าน assignment
อาจารย์ครับปกติการบ้านนี่ถ้าเราทำไม่ได้เราทำไปแค่ข้อที่เราทำได้อาจารย์ว่าอะไรไหมครับ
ไม่ได้นักศึกษาต้องพยายามทำให้ได้นะ ข้อที่ทำไม่ได้มันมีข้อไหน
คือมันเรียนทุกวันเลยครับอาจารย์แล้วมันได้ทำแค่เสาร์อาทิตย์เองครับ เวลามัน
เหรอ
ไม่พอ
เหรอ
เพราะว่าใช่ครับเพราะว่าช่วงใกล้
คุณ
สอ
ก็
บ
มีกันตั้งหลายคนเนี่ยคุณก็แชร์กันสิ คนนั้นทำหนึ่งข้อคนนี้ทำข้อนั้นข้อนี้แล้วก็เอามาดิสคัสกัน ถ้าทำคนใดคนหนึ่งบางทีก็ด้วยอะไรนะอย่างที่คุณว่าแหละบางทีมันก็เวลามันก็จะน้อยหน่อย
อาจารย์พอจะเป็นไปได้ไหมครับว่าแบบให้ส่งอีกครั้งหนึ่งอะไรเงี้ยครับเพราะว่ามันไม่ทันจริงๆอะครับอาจารย์
ส่งอีกครั้งหนึ่งคือส่งเมื่อไหร่อ่ะนี่มันจะสอบมิดเทอมแล้วอ่ะ
ก็เดี๋ยวยังไงก็ต้องอ่านหนังสือก็ขอเป็นก่อนมิดเทอมได้ไหมครับอาจารย์ วันไหนอาจารย์ก็ลองกำหนดมาดูก็ได้ครับ
เหรอก่อนมิดเทอมนี่คือวันที่10ใช่ไหม
วันที่10ครับ
ไม่รู้คนอื่นว่าไงนะฮะไม่รู้คนอื่นว่าไง
ได้ครับอาจารย์
ได้คือยังไงฮะ
ก็ยังไงเนื้อหาที่เป็น assignment ก็ต้องอ่านอีกรอบอยู่แล้วครับผมเพราะว่ามันเป็นอันเดียวกับที่สอบใช่ไหมครับ คือ
ใช่
ก็ถ้าคนไหนยังไม่ส่งก็ขยายเวลาให้เขาก็ได้ครับ เป็นก่อนสอบ
เหรอ
ครับ
เหรอ
ผม
จะต้อง
ใช่ครับ
ส่งก่อน
เห็นด้วย
ส
ครั
อบ บนะฮะเพราะว่าถ้าคุณไม่ส่งก่อนสอบแล้วคุณไม่มีทางทำข้อสอบได้ เพราะข้อสอบจะเป็นอีก
ใช่
ส
ครับ
เต็ปหนึ่ง above ไอตัว assignment ไปอีกหน่อยหนึ่งนะฮะ
ก็จะได้ทบทวนด้วยครับอาจารย์ ก็มันก็ดีหลาย ๆ อย่างครับ
อะไรนะ ตกลงยืดเวลาไปอีกหน่อยล่ะ
ครับ ก็จะได้ทบทวนแบบด้วยครับว่าแบบแบบข้อสอบปัดจะน่าจะประมาณไหน
ไอ
อะไร
ไอ
อย่างเงี้ย
assignment ล่าสุดนี่มันส่งวันไหนอ่ะ ผมจำไม่ได้
ส่ง
เมื่อ
เมื่อวา
คื
น
นเมื่อวานนะครับ เมื่อวานคื
คื
น
น
ครับ
อ๋อ เมื่อคืนใช่ไหมฮะงั้นอาจจะถ้าคนที่ยังทำไม่เสร็จอาจจะยืดให้ถึงสักวันที่10แต่ว่าวันนี้เนี่ยเดี๋ยวผมจะมีชุดใหม่อีกอันหนึ่งนะ ให้ไปอีกทีหนึ่ง
ครับผม
นะฮะ
ครับผมครับผม
นี่เดี๋ยวผมจะมีชุดใหม่ให้เพิ่มไปอีกนะครับเอาจริงๆผมกำลังจะเตรียมว่าจะมานั่งดิสคัสเรื่อง assignment พอดีเลยอ่ะเพราะถ้าทำไม่เสร็จมันก็ยังดิสคัสไม่ได้สิ ว่าข้อไหนอะไรยังไงหรือยังไงดี
ก็ assignment 1 ก็น่าจะได้อยู่มั้งครับอาจารย์เพราะว่า assignment 1
assignment
ก็ส่งอาทิตย์ที่แล้วตั้งแต่อาทิตย์ที่แล้ว
assignment 1นี่คือเดี๋ยวนะฮะ assignment 1เอ๊ะทำไมผมหา assignment ในนี้ไม่เจอเลยมันหายไปไหนหมดอืม assignments number 2 due yesterday เอ๊ะแต่ assignment 2นี่ก็น่าสนใจนะเห็นหลายคนก็ส่งมาแล้วนะ
ของผมก็ส่งไปครับอาจารย์แต่แบบทำไม่ได้ครบทุกข้อทำข้อที่ทำ
อ๋อ
ได้
เหรอ
ครับ จริงๆก็
อ่า
ดิสคัสเลยก็ได้ครับอาจารย์เพราะน่าจะมีคนทำเสร็จหลายคนอยู่ครับ
มันยังดูไม่ค่อย complete เลย มีใครทำเสร็จแล้วมั้ง
จ้าครับงั้นถ้าวันนี้เป็นแบบ discuss assignment 1แล้วอาทิตย์หน้ามันอาจารย์จะยังสอนอยู่ไหมครับอาจารย์
อาทิตย์หน้าเหรอ
ใช่
ไม่
ก่
งั้
อน
นก็
วัน
เอา
ที่
พร้อมกันอาทิตย์หน้าไปเลยดีไหมมันจะได้ทีเดียว
โอ้อาจารย์สอนทันป่ะครับ assignment 1 assignment 2 assignment 3อาจารย์จะ discuss ทันป่ะครับ
ทันก็เราจะไปดิสคัสทุกข้อทำไมล่ะ เราก็เอาข้อที่มันมีปัญหาก็พอ
อาจารย์แต่อาทิตย์หน้าเข้าสอบช่วงสอบแล้วไหมครับ
อาทิตย์หน้าเราสอบวันที่อะไรวันที่11อ่ะ15ไม่ใช่เหรอ
แต่ก่อนหน้านั้นน่าจะมีค
หมาย
น
ถึง
สอบ
ก่อนหน้านั้นวิชาอื่นนะครับ
ก่อนหน้านั้นยังไงเอ่ย
เพราะว่าช่วงสอบมันเป็นช่วงวันที่10 ถึง 17นะครับอาจารย์ช่วงมิดเทอม
ใช่ใช่ใช่
บางคนเขาน่าจะมีสอบนะครับ
อ๋อเหรอfirst assignmentไม่งั้นเดี๋ยว assignment เราเก็บไว้ก่อนดีกว่าทีเดียวคราวหน้า แต่ว่าอาจจะเป็นช่วงวันไหนสักวันหนึ่งพฤ
งั้น
หั
อา
ส
จารย์
เช้าสอบไหม
วันงั้นอาจารย์ก็ต้องเป็น next week ที่แบบไม่มีสอบกันนะครับอาจารย์ต้องแบบเร็วๆ
วันไหนล่ะ มันจะได้ทีเดียว พอดีผมจะสะดวกกับคอมพิวเตอร์อีกเครื่องหนึ่งมากกว่าด้วย เอาวันไหนดี
คือถ้าเป็นพฤหัสหน้ามันวันที่11ผมไม่แน่ใจว่าเพื่อนๆเขาจะมีสอบวิชาอื่นกันไหมอะครับผม
หนูมีสอบ
คน
ค่ะอา
สอ
จาร
บ
ย์วันที่11
อะไรนะ มีสอบหรือเปล่า
วันที่พวก
หนูมี
ปีสาม
ค่ะ
มีสอบแล้วค่ะอาจารย์
มีสอบวันที่11เอาวันไหนดีเอ่ย
อาจารย์แล้ววันนี้ช่วงบ่ายอาจารย์ได้ไหมครับ
วันนี้บ่ายใช่ไหม
ผม
ตอน
อยาก
บ่าย
ให้
ก็ได้
เลื่อน
ถ้าอย่างนั้นตอนบ่าย ต่อจาก
แต่
ไอ้
ว่า
ชั่วโม
แต่
ง
ว่า
แลบอะ
ถ้างั้น assignment ก็ยัง assignment 3 กับ 2 ก็ยังไม่ก็จะส่งใหม่ไม่ใช่เหรอครับอาจารย์ ก็
ใช่
คือ
ค
ยั
รั
ง
บ
discuss ได้แค่ assignment 1 ก็
ใช่
discuss ตอนนี้ก็ได้ค่ะ ถ้าจะ discuss ตอน lab อะ
เอาชั่วโมงแลบไว้แล้วกันเนาะ เอาเท่าที่ได้ก่อนแล้วกัน แล้วก็เท่าที่อุปกรณ์ เดี๋ยวเราจะเอื้ออำนวยนะ เผื่อถ้ามัน complete ไปแล้วจะได้ไม่ต้องอะไรมากมาย ไม่ต้องนัดอีก ถ้ามันไม่มีอะไรเพิ่มเติมนะครับ คิดว่าหลายคนบางคนก็น่าจะทำเสร็จแล้วเหมือนกัน เดี๋ยวเอาเป็นช่วงบ่ายกันแล้วกันนะครับ ถ้าอย่างนั้นเดี๋ยวช่วงบ่ายลองดูก่อนว่าถ้าเกิดว่ามัน complete ก็จะได้อันนี้ไปเลยนะฮะเพราะฉะนั้นเดี๋ยวเช้านี้ขอกลับมาที่ไอ้ตัว lecture ก่อนแล้วกันเนาะ ถ้าอย่างนั้นนะฮะตรงนี้มีคำถามไหมเอ่ย มีคำถามไหมครับเกี่ยวกับHardy clause นะ Do you have any questions relevant to the Hardy clause method? So if no, we'll move to the next chapter. The next chapters, the midterm examinations will be covered up to the Hardy clause method. So I will just have a look again in the chapter 4. What do we leave? In the class material. So just come back to the chapter 4. But I think we have already completed. But just to make sure that okay. So it seems like the Hardy clause methods is the last topic of this chapter. So the midterm examinations will cover up to today's lectures. And if you don't have any question, then we move to the next chapter. The next chapters actually it's the chapter 5, but according to the titles of the presentations, it's written the chapter 6 because previously there was the chapter 5. The chapter 5 we talk about the sewerage collection system, but I think after I check the contents of the course, our course and other course, there are some overlapping in terms of the course contents, and for the sewerage collection systems, I think it's already there in some other course in hydraulic engineering, or maybe part of elective course something. That is why, so I just removed the chapter 5. So this chapter finally becomes a chapter 5. But anyway, this chapter is a big chapters. So if you really go through the presentation, you will find this chapters contains up to 218 pages. It's quite a big chapter. So we will spend a lot of times after the midterm examinations talking about these topics, the water treatment process. So why we have to do this? If you come back to if you come back to the very beginnings of the class that I have talked about the urban water cycle. So now it's all gone, what I have written in the morning. Okay, just come back to this figure. This is the urban water cycle that we are really familiar with. According to the urban water cycle, so we withdraw raw water from probably Chao Phraya River, just in case of the Bangkok. Then these raw waters we send to the water treatment plant, and then from water treatment plant, the purified water is distributed to each individual household where the water distribution system. So in the previous chapters, we just talk about the some part of the distribution system, pumping system, storage capacities. We also talk about the piped network. You can determine the flow rates by applying the Hardy-Claus method. And then after that, the water after use becomes a wastewater. So wastewater need to be collected through the sewerage collection system. Actually, the sewerage collection system was supposed to be a chapter 5, but I just removed it. So if you study this chapter, so it will be a long story again. We don't have sufficient time to talk about it in this course. Maybe you can look for other course if you're really interested. And then wastewater coming from the communities will be again sent to the wastewater treatment plant. So we treat the wastewater here, and only the treated water will be discharged back to the rivers again. So it's just like a cycle. So this cycle we normally call a water cycle. So before the midterm examinations, we have completed the topics talking about the raw water intake. We have completed the topics talking about the water distribution system. So what we have left is just the details of the water treatment plant, water treatment process, and also the wastewater treatment process. So after the midterm examinations, we will focus more in details about the treatment process, both water treatments and wastewater treatments. And at the end, we will talk about how we deal with the sludge generated from both the plants. Wastewater treatment plant generates biosludge, but water treatment plant generates a lot of inorganic sludge coming from the coagulation and flocculation process. So we will talk about this process in details. That is why in the chapter 5, we'll focus more in water treatment process. And then after we finish this chapter, we will talk about the wastewater treatment process in the next chapter. At the end, before closing the sessions, the class, we will talk about the sludge treatments. So we spent like almost 6 weeks to talk about the water treatment plants, and then 1 week, probably 1 or 2 weeks, probably for the wastewater treatment plants, and just 1 week for the sludge treatments. So now we will be with this chapter for almost 2 months. That is why this chapter comes. Before talking about the water treatment process, so if you really look into the background about the pollutions and impurities, we can actually classify the pollutions and impurities into 3 categories based on its fates or status. We can actually classify the pollutants based on the physical characteristic. Physical characteristics means we talk about the status. The pollutants or the impurities may exist in water in a gaseous form, in a liquid forms, or in the solid forms. That is why we determine the solids in water. So after the midterm examinations, we will begin the labs with the solids determinations. And the pollutants or the impurities which comes in a liquid forms, for example, oil and grease. Oil and grease is also a liquid. So once it gets into the water, though they're hydrophilic substance, but if they're there, they're always creating the problems. That is why we have to remove this oil and grease from water. The gases, for example, carbon dioxide. We all know that carbon dioxide we may find a lot in groundwater, as the groundwaters may get dissolved because the water is not exposed to the atmosphere, so that the oxygen may not be able to get into the groundwater. So groundwater, there will be problems with the carbon dioxide dissolved, and this will create the acidities and causing the corrosions in the piping systems. For the there's mistakes here. It should be a chemical, and this box it should be a biological. For the chemicals, in terms of the chemicals point of view, we can actually classify the pollutants into, for example, organic or the inorganic group. Organics means the pollutants essentially consist of the CHO and S, the basic elements, and the inorganic normally refers to the ions like positive charge ion, metals, heavy metals, or even a negative charge, which come along or associated with the positive charge ion. Chloride is also the inorganic, and they actually present in water a lot during the dry seasons. So classification based on organic or inorganic usually refers to the chemical point of view. But for the biological, according to the biological characteristic, we can actually classify the pollution into probably pathogenics or the non-pathogenics. Pathogenic substance mostly refers to the microorganisms which has the potential to cause the disease. Not all the microorganisms has the potential, but some potentials, only some potential can actually cause the disease. So those microorganisms we call the pathogens. But for the microorganisms which do not have ability to cause the disease, we normally call the non-pathogenic substance, or it may be the non-living things. So we classify the pollutions or the impurities according to its characteristics like this. Why we have to treat the water? We treat the waters because we want to separate the impurities or the pollutants out from water. Basically, the procedure of the processes that we are going to talk about within this chapter, they are really based on the separation concepts. For example, sometimes we have to separate the solids from liquids. Sedimentation, for example, is the unit operation uses to separate liquids from solids. Separations of the liquids from solids you can find in both water and wastewater treatment. And then the next one is the separations of liquids from solids. So the first one is solids from liquids, but the second one it's reversed. It's the liquids from solids. So for example, sometimes we need to remove the water from the sludge. The sludge is actually the solids matter left over, or it's actually the byproducts of the water and wastewater treatment. So the sludge, it comes like a slurry at the beginning, but we want to remove the water as much as possible so that the sludge become a cake. So once it becomes a cake, so it's easy to handle. So we can put the sludge cake into a sack or a container and deliver to somewhere and dispose it somewhere. So if it's exists in a slurry form, so it may be very difficult to handle. That is why in the sludge treatments process, the ultimate goal of the sludge treatments process is to separate water from the sludge, or separate the liquids from solids. Sometimes we want to separate liquids from liquids, like separations of oil and grease from wastewater. Especially wastewater from canteen contains a lot of oil and grease. In fact, the shops vendor, they are encouraged to handle the oil and grease in wastewater. So the university normally provide them the oil and grease separator, and these oil and grease separators are equipped at almost every food court, but we are also expected them to remove the oil and grease once in a week, but they had never done it. That is why the oil and grease separators at the end becomes useless. We don't want the oil and grease go along with the wastewater. We normally treat the oil and grease as the solid waste, not the wastewater, because if it goes to the wastewater treatment plant, so it may bind with the microorganisms cells. So finally, microorganisms can actually not get the food, which will finally affect the efficiencies of removal or the efficiencies of treatment. Sometimes we separate the gas from liquids. Like the decompositions of the organic matters in wastewater, a lot of carbon dioxide will be formed. I have written the equation many times. The organic matters plus oxygen becomes carbon dioxide and water molecules. So carbon dioxide is produced. So once the carbon dioxide is produced, it may not be good if we dispose of that wastewater or water along the pipe, especially the steel pipe. So it may cause like the oxidation of the pipe, and finally the pipes become corroded. So we have to separate the gases from liquid in this case by blowing the air into the water sample, so that the carbon dioxide, which remains in a small quantities, will be coming out from the water sample. We call the purging system. These are the list of the unit operations and unit processes used in water and wastewater treatments. You may have seen it sometimes when we talk about the introduction. You may be seen like the flow diagrams. All the flow diagrams for water and wastewater treatments begins with the screens. The screen is normally used to separate the big objects, the floating objects, or maybe a living organisms come along with water. We use the screens. The principles of the screen working is very simple. So we provide the screen with the specific opening size for the trash or the impurities which has the size bigger than the opening size of the screen will definitely retain it in the front of the screens. Only smaller size will pass through, including waters and the dissolved forms. So the screen is always located, is always used in both water and wastewater treatment plant. And sometimes we apply this one just to prevent the things that may get stuck into the mechanical equipment uses in the treatment plant. Especially sometimes we need to protect the pumps, we need to protect the mixer. So if there is the big objects, or if there is like a coarse particles or fine particles, sand particles, it may cause abrasion to this equipment. That's why we have to remove it at the very first, at the beginning of the treatment process. The next one is the comminution. Comminution is also the mechanical equipment we use to cut the objects, from whatever the size that comes along with the water to becomes a uniform size. So once it left, once the impurities leave the comminutor, so it becomes a uniform size because it's getting cut. Grit removal is basically the chamber we use to precipitate the sand particles or the grit particles, gravel, small gravel, so that these particles will not get into the plants and will not jam or will not interfere the pumps while working. Aeration, as I mentioned previously, sometimes we have to remove the carbon dioxide so that this carbon dioxide will be removed if we blow the air instead. Mixing, especially for water treatment plant, we need to apply some chemicals. We need to apply some coagulants, which are the alums or some other types of the coagulant, so that the mixing equipments are required just to enhance the collisions or enhance the chemicals to reach each elements of water. Sedimentations, it's placed after the coagulations and floculations, and for the wastewater treatment plant, we allocate sedimentations right after the biological reactor so that solid particles can actually settle in the tank, and we finally remove these solid matters as the sludge. Flotation is something different, something opposite to the sedimentation. Sedimentations actually this process, we take the advantages of the gravitational force. The gravitational force will bring all the heavier particles to the bottoms of the chamber. But for some particular types of the particles, they actually have the density more or less the same or comparable to the water. So water density is approximately 1 kilograms per liter. But some types of the particulate matters, they also have more or less the same densities. In this case, if we are waiting for the particles move down in the sedimentation tanks, it may take a long time, or it may be not possible. That is why we do the opposite way. So as they are very light, so we make them lighter. So we provide the air bubble. So we supply the air bubbles at the bottoms of the chamber. We actually create very fine bubble. The bubble size is just 0.1 or 0.2 millimeters. So these fine bubbles, once it blow out from the air blower, so it will get attached to the particles and makes the entire densities lighter. And finally, this bubble will bring the light particles to the top or to the surface. Then we apply the skimmer to remove these suspended matters, light suspended matters from the surface. So we do the opposite way for the flotations. I mean, as compared to the sedimentation tank. Adsorption is a process where we used some kind of adsorbent to adsorb the pollutants. Pollutants is just adsorb. Adsorb, AD, means just a stick onto the surface. Mostly we use the activated carbon to adsorb the pollutants or the impurities came along with water. So it just adsorbs, or it's just a stick on the surface of the adsorbent. So you may familiar with the, you may know about the activated carbon. So I'm sure that you have the water filter at home, and many houses has this kind of equipment. You have water filter, tapped water filter, because you are not sure whether the tapped water is safe for the consumptions or not. That is why many houses in Bangkok we equipped with the water filter. But anyway, inside that filter, mostly they are the activated carbon. They are not just the sands or gravel. They are mostly the activated carbon. So activated carbon, they do the filtrations, but they also do the adsorption. The main removal process is the adsorption. So if you are talking about the activated carbon, so they are able to adsorb the pollutants. So adsorption is more or less used in the advanced treatment process of the tertiary treatment process. Normally, we do not apply this process at the water treatment plants or the large capacities productions because it's very costly. Although we are sure that they can actually produce very good qualities of water. But anyway, it is very pricier. We have to change the activated carbons within the specified times. And longer than the specified time, it may not give a better efficiency. That is the limitations of the activated carbon, which carry out the adsorption process. Adsorption, the spelling, just watch the spelling. It's AD, not AB. You may familiar with AB. AB is the absorption. Absorption is different from the adsorptions AD. Absorption AB is refers to something get inside. For example, the bacterial cells, they absorb the food from the outside cell in the solutions. That one is absorb AB. But absorption, nothing penetrate through the membrane or penetrate to anything, but just stick it onto the surface. That is why we divided this as the adsorption, not absorption. This is the technical term. Adsorption is the technical terms, okay, not the common terms. Filtration is probably the last unit operation that we used. After filtration, the water, the treated water will just be kept in the clear well, so that we apply the choline just to disinfect the water, and this clear well we just keep water before distributing to the distribution systems. So these are the most commonly used unit operations and unit processes in water and wastewater treatment. And some units are only used in water treatment. Some units are only used in a wastewater treatment. Disinfection is a must for the water treatments, but it may be alternative to the wastewater treatment plants, because the treated waters, we don't have to actually kill all the germs. The germs may be there, but it won't create any harms to the human being. We just dispose the treated waters into the natural receiving stream. So natural receiving stream will purify these pathogens by self-purification process. Because if we learn it about the disinfections, you will find there are two factors that influence the performance of the treatments. One is the times, and another one is the temperatures. If we actually could maintain at high temperatures, we can shorten the times to disinfect the germs. But if we don't have facilities, heating facilities, we may keep the waters for like 2 or 3 weeks. Then our waters will be saved to release or discharge it to the natural receiving stream. So I'm talking about the wastewater. So some units are basically used only at the water treatment plants, but some units are only used at the wastewater treatment plant. Okay, so these are the most commonly used unit operations and unit processes. For the treatment types, we can actually classify it into actually 3 major types, but here there are 4 treatments, major treatment processes. Physical treatments, it's actually nothing but just the separations based on the physical properties of the contaminants, shape, size, the weight, applying only the physical methods to separate. Like in a screen, we provide that screen with a small opening pits, so that whatever the larger objects which come along with water, we get stuck in the front of the screen. So this is a kind of a separation based on the physical characteristic. We can actually consider the pre-treatment methods as the physical treatment methods. But after performing physical treatments, water passed through the screen, passed through the grid chamber, and passed through properly the primary sedimentation tank. Even 3 or 4 processes are done, but still there's some contaminants left in water. Mostly the contaminants with a very small size present in water. For example, the colloidal particles. We know that colloidal particle is there because the water is not clear. But how can we remove these contaminants? We cannot wait for so long. Even we used the sedimentation tank, but still it never precipitated. So in that case, we have to modify the surface characteristic or modify the chemical properties. And these properties, once it gets modified, so it will be easy to be removed. So just like the coagulation and flocculation process, we apply the positive charge into the water, and this positive charge will react with the colloidal particles in the surface, near the surface. So finally, the charge will be not neutralized, and once the charge becomes neutralized, we can actually coagulate them. We can create the bigger flux. Then we can let them settle to the bottoms of the chamber. So these are the kinds of the physicochemical treatments. Filtration is also considered as the physicochemical treatments. Physicochemical treatments is widely used for treating water or for producing a water. Biological treatments is another treatments methods. These schemes is actually works with the waste containing the organic compounds. Waste with a higher organic compounds, it is recommended to use the biological methods, because the biological methods is nothing but just try to do the same thing as the nature do. The nature, they have ability to clean up themselves. If we discharge water into the rivers, water qualities in the river does not showing any signs of the waste contaminations. So in that case, it proves that the nature, they have their own capacity to remove the waste by themselves. So we call this as the self-purification process. But in wastewater containing a high organic substance, in this case, before releasing the wastewater into natural receiving stream, we need to remove the organic substance from water itself by using the biological treatment methods. The biological treatment methods means the methods that relies on the microorganisms, especially the bacteria. So we let the bacteria degrade the organic substance and utilizing the oxygens as the electron acceptor before converting them to the harmless end products like water molecules or carbon dioxide molecules. So these are the biological treatments process. So for biological treatments process, we will talk about this in details in the next chapter. So in this chapter, we will focus more on the physicochemical process. The last one is the thermal treatment. The thermal treatment is actually the process where we use the heat to remove the pollutant. Sometimes we use the heat to remove the pollutants. For example, in the sludge treatments, we apply the heat to clean up the sludge, because very often we really experience the sludge gets fully covered by the oil and grease or some kinds of organic substance. So if we apply the heat, all this oil and grease will break out, then it will not cover the sludge molecules again. So the sludge become easier to handle. But anyway, the thermal treatment is not very popular because it's the energy consumption process, high energy consumption process, and also dealing or handling the heat. It's never been simple. That is why we are trying to avoid using this process. But anyway, it could be one of the types of the treatment process uses sometimes. So these are the flow diagrams showing the physical treatment process. Physical treatment process essentially consists of the screening, precipitation, flotation, filtrations, and the last one is the centrifugations. So the precipitations, in fact, you can use the sedimentation. Sedimentation would be a better idea in this context, because sedimentations is the particles just settled to the bottoms of the chamber. But precipitation normally refers to substance A reacted with the substance B and then form the precipitated forms. So precipitation refers to the solid matters generated by the chemical reactions or probably the biochemical reaction. That is why we never use the precipitation in the general point of view. We prefer to use the sedimentations. I mean, I'm talking about this gas. Filtration. Filtrations also consist of several processes: membrane filtration, ultrafiltration. But the most commonly used at the plants, both water and wastewater treatment plants, is the clarifying filtrations. Water is kept in a filter and we allow them to move down through the opening pit. So for the filter, we can actually classify it into two types: slow filters, rapid filters. Slow sand filters or rapid sand filter. Do you have any idea what are the key parameters which makes the filter becomes slow or rapid? Do you have any idea? So if we have like a filter, just like a columns, and inside we put the sand, and on the other hand, another columns we put the cover. The size could be like a approximately 1 centimeter. So which one will provide a rapid filtration rate? If I'm asking like this, of course, the filter with the bigger size will definitely providing the higher filter rate, filtration rate. So the filters with the larger size normally provide rapid filtration rates. So if we use the larger filter size, it means that you will be getting high filtration rates. High filtration rates, sometimes we call the high filtration rates filter. Sometimes we call the rapid sand filters. But low filtration rate, sometimes we call the slow sand filter. Just call it, just to make it easy to call rapids and slow. So the key factors is just the media sized, sands, anthracite. So these are the media. We generally call the media size. Centrifugation, sometimes we use it, but not very common, because centrifugations is actually not suitable for the large production capacities plants. Only small plants may be used. The centrifuged. Centrifuged, we have to put all the waters into this machine, and then it takes. I mean, the centrifuge normally it's not that large, but if we have to treat water with large quantities, we may have to end up with the problems, some problems due to the capacities. Biological treatments is in fact bacteria or the microorganisms utilize the organic substance. If they use the oxygen, so we call that process as the aerobic treatment. But if they just are produced, they just degraded without providing the oxygen. In this case, we call this process as the anaerobic treatments or anaerobic process. And for the aerobic treatments, there are a number of the process that we used in reality. Because actually that sludge process or aerobic process, we have been using this process for water and wastewater treatments for over 100 years. A thermal treatment, evaporation may be one of the methods, or incineration. This is also another treatment process. Mostly thermal treatments we apply it to the municipal solid waste. We don't apply, we don't use it regularly for the water treatment. Incinerations, it's a kind of the process where we burn the trash so that we finally get the energies. Evaporation, you may have heard about the news several days ago. There was two problems about the salinity in the Chao Phraya River. So in this case, the Metropolitan Water Works authorities, they said the tap water can actually be consumed, but just the taste may be a little bit salty. So if you want to remove the salt from water, so what you can do? You can actually evaporate all waters, and what is left is just the salts. This is actually the conventional methods we use to separate the chloride from water. We apply the heat to treat that water. But the problem is the waterworks authorities, they don't have such a facilities to evaporate all the waters, million cubic meters per day. That seems to be impossible. That is why most of the plants, they are not interested to locate the thermal treatment facilities because it is very costly and it may not be very convenient or it may not be very good for the large production plant. In water treatment, these are the list of common contaminants found in raw water. Floating object, algae everywhere, especially the ponds. There are a number of algae species, excessive iron sand manganese, and probability hardness. These parameters were found in a significant amount, especially in water treatment in groundwater. For the iron sand manganese, if we want to remove the iron sand manganese, we have to expose waters to the atmosphere so that the oxygens will get reacted with the iron sand manganese, becomes iron oxides and manganese oxides. Both iron oxides and manganese oxides are the precipitated forms of the Fe3 and Mn4. So precipitations will actually occur if we just expose waters to the air. We don't have to pay any extra amounts of chemicals added. So just expose them to the air. Make them like a tray aerator. Suspended solids, of course, we have to remove them. Where a sedimentation tank and dissolved gas, we apply the air aeration process to change the gas contents or to remove the gas which may cause the problems to the piping systems. Taste, odor, color. These parameters are really difficult to be removed from water. Both three parameters, all the three parameters, taste, odors, and colors. Just imagine how would you remove the colors from the tea? If you really drink a tea, so how would you remove the colors from the tea? That would be very difficult. So the only way we can apply is the use of the activated carbons. So activated carbons will provide an absorption process. Organic bacteriological pollution. So this one is also the one of the substance commonly found in water. For the organic substance or bacteriological pollution, we may have to apply the disinfection process to remove them from water. The objectives of the treatment, why we have to treat the waters. I'm talking about the water supply. For water supply, we have to treat the water just to protect the consumer's health from the contaminations of the germ, so that the people are really safe while drinking or while consuming water. Sometimes you have to make it acceptable for the consumers. That is because some consumers, they try to object the waters containing color, waters containing some kind of unpleasant smell or taste doesn't look good. So people try to object to use that water. That is why sometimes we have to make it acceptable by the consumer so that they feel comfortable to consume or to eat. Sometimes we have to treat the waters for economical reasons. For the economical reasons, for example, prevent the scaling and the corrosions in pipeline, or probably staining cloths during laundering. You may know about the boilers. Almost every industry has the boiler. Our hospital also has a boilers. Why the boiler is really important to the industry? Because they use to generate the stream. The stream can be applied for several purposes. In the hospital, they need the stream, hot streams, just to inactivate the microorganisms. So sometimes we have to use the boilers. But the problem with the boiler is that the boilers is the equipment where we use to convert the waters in the liquid status to the vaporizing forms. If we boil the water, of course we get the a stream. But if we boil a hot water, what will happen? Hot water, once we boil, then some of the calciums and magnesiums will be precipitated, or we can say that the hardness will be removed, because they are all temporary hardness. They are not the permanent hardness. So once we boil, so it becomes the precipitated forms. So if it precipitated in the tubes, in the boilers, and for some times that tube scaling of water gets stuck, get clogged, so it caused the damage. Finally, it caused the damage. Boilers cannot be functioning. We have to just stop using that boilers and look for the new one. So it's very costly, and it also create a lot of time lost That is why we have to prevent some things that may happen, like scaling or corrosions in the pipeline. So this is the reasons why we have to treat waters in terms of the economical reasons. In some cases, we have to add it to the source where there is no sufficient impurities, which may be good for consumptions or good for people to use that water. For example, we have to add the oxygen by the aeration. We prefer the waters containing some certain amount of oxygen dissolved. And in some areas, there are really shortage of the fluoride, so that we have to add some fluorides into the waters. But luckily in Thailand, we don't have to do it, because many water resources, especially in the northern part of Thailand, already contains large amounts of fluorides. So we will experience too much fluorides, not the too less fluorides in water. That is why some areas, some countries, they may add, but in Thailand, we are not interested to add the fluorides, because we already have a lot in natural water resources. So if you drink the fluoride water with a high fluoride, what will happen? So you will end up with the dental fluorosis. But if too less the fluorides, of course, you also have the problems with your teeth. So too much is also not good. Too less is also not good. This kind of elements. The choice of treatments. In the previous slides, I have shown you several unit operations and unit processes which are commonly used. But anyway, we don't have to go for all. We may need only few unit operations just to purify the water. But in some cases, maybe we need more than 10 unit operation to purify. But this how can we actually make a judgment? So which one is important, which one is unimportant? Anyway, it depends on the qualities of raw water. If the raw water qualities is already good, for example, groundwater, in this case, you don't have to do anything. Groundwater, if the hardness is not too high, we can just apply chlorine just to disinfect, so that it's all for the treatment. But for the Chao Phraya River, for example, if the raw water is the Chao Phraya River, so you have to handle huge amounts of the suspended solids which come along with water. We have to consider some of emerging pollutants that may exist in water. We have to consider the possible pollutants that may get into the water. So it depends on several factors. Qualities of raw water, required qualities of filtered water. So if we are saying we want to produce that water just to for the daily consumption, it is okay. Water supplying, you can actually consume. But if you want to do more, the water quality must be meet some drinking water standard. So we have to go for another levels. In some countries, they have made they have a very stringent effluent qualities. In Thailand, the COD, chemicals oxygen demand, we require to be less than 120 milligrams per liter. That is good enough. So as long as the wastewater contains the COD less than 220 milligram per liter, that one is good enough. But in some countries, like in Vietnam, I'm not sure, in some particular areas, they have make up the standards, effluent standards, much more stringent. They make like only 60. So 120 is not enough. The effluents must go below 60. So in that case, we may have to apply some special process to bring the COD value according to the first standard. So it has to be only 120, but according to these standards, it has to be less than 60. So special process is required. So it depends on the required qualities of the treated water. Economical reasons, as I have already mentioned. Sometimes it also depends on the parameters, treatment parameters, what parameters we are really interested. So if we are really interested in the BOD removal, then we have to apply a unit operation which are capable to remove the BOD or the nitrogen and phosphorus. If we have if we concerns about the eutrophications in the lake and our receiving treated water is the lakes, in that case we have to provide the facilities to remove the nitrogen and phosphorus. So these are the ideas of selecting the unit operations and unit process. We don't have to go for all because it's not necessary. Raw water sourced, mostly we use the surface water. In Thailand, we use the surface water, but in rural areas or the village outside the local municipalities area, they may use the groundwaters. They may have facilities for withdrawing the waters from underground, so that they use mainly the groundwater. They make a well so that waters can be withdrawn from the well. The spring, the ocean water, the oceans can be our source, but it is very costly to remove the salt from the sea water. The treatment system, the thing is, we really need to have treatment facilities. It's not possible to have a treatment facility treating all types of wastewater. It's not possible. In the past, actually, the Ministry of the Public Health, they make a mistake. They launch the standard design for the wastewater treatment plants at the hospital. But even the hospital, they are also producing different characteristics of wastewater. So it cannot be the same. So these treatment plants may be working very well in some hospital, but in the other hospital it may not be working because different patterns of living, these different patterns of the working, so that the wastewater coming from the hospital will be different. So it's basically we need to design separately. Water treatment plant is very specific to the required water quality, as I mentioned. Okay, so the next 4 or 5 slides are the typical flow diagram for the water treatment plant. This one is the flow diagrams for the surface water treatment plant. Just begin it with the coast screen, followed by the aeration, coagulation, circulation, sedimentations, filtrations, and disinfection. For the sludge generated from the sedimentations, we have to handle whether we go for the sludge thickeners and use the dewatering machine or apply the sludge onto the sand bed, so the sludge is spread all over the drying bed due to the heat from the sun. So all the water get evaporated. Only the sludge dried on the surface. Then we can remove it. We can handle it finally. So this one is the typical flow chart of water treatments. The aeration is nothing, just like a cascade. So water is flowing from one step to the another step, falling down, and during it fall down, the water becomes very thin films, so that the air containing the oxygen can actually get into the water. And finally, once the oxygens get into the water, so it changed the chemical conditions from reducing conditions to probably the oxidizing conditions. Some of the contaminants will get precipitated once the oxygens react. These diagrams also compare various types of raw water. As I mentioned, so if you use the underground water, the only process need is just the disinfection. But underground water with a very hard water, sometimes we have to apply the softening process to bring the hardness down to the proper range. And at the end, apply disinfectants in the disinfection process. For the surface water, other types of the surface water, upland, lowland. The uplands, the quality is expected to be better than the lowland. So some process may not be required, but for the lowlands, all the process are required until the disinfections before sending the treated water to the community. This is also the typical surface water treatment system. Basically contains some chlorination process at the very beginning. This one we generally call the pre-chlorination. In the disinfection, so if we use the chlorine again, the chlorine applications here, normally we call the post-chlorination. If you apply the chlorine at the very beginning, this unit is called the pre-chlorination. At the end, it is the post-chlorination. So we will talk about that again, why we really need the pre-chlorination. Surface water is the same with the previous figures, but just one unit operations added. Here is the storage tanks. Why we need to have the storage tanks? We have already discussed about in the last week. We need the storage tank just to regulate the flows, and sometimes we need this tank just to control the raw water quality. Okay, so I think now the time is coming up at 12:30. We have already spent 3 hours for the today's lectures, so that we'll meet again in the afternoon for the lab sessions. In the labs today, there will not be any labs. There will not be any quizzes. So if you have anything to do in the afternoon, you can absent. But we will discuss about the report last week. There are some interested points to be discussed in this afternoon regarding to the reports that I gave it to you, the results that I gave it to you last week. And after the report discussion, so we will come back to our assignments again, so that we can discuss some assignments, some question that maybe what that may be difficult, or I don't know, or maybe questionable you'd like to ask. Okay, so we will do it after the discussion about the lab results. Okay, we meet again in the afternoon. This afternoon, let us meet at 1:30. Okay, at the same time as our regular time. Okay, so for today's morning, do you have any question?